talk a little bit informally about opportunities that I see in particle physics that could potentially be exploited for interstellar propulsion applications, power and propulsion. This is really a compilation of the thoughts that I've had and professed informally to friends and colleagues ever since I was in graduate school, with a few updates from some of the more recent developments that Les has already alluded to and some others. Okay. It does insist on doing something other than what I want to do. From my perspective, deep space flight, and in particular interstellar propulsion, has got three main enabling technologies. First, of course, we have to have a propulsion system that's adequate to the job. To make the propulsion work, we have to have power. And the third thing we have to have is some sort of structural material or some sort of energy field augmented structural material that can handle the stresses involved from the high acceleration and from the radiation that's encountered during transit of interstellar space, where the ship is plowing into neutral gas at relativistic velocities. My long-term belief, and frankly one reason why I went to particle physics, although I sort of surveyed the sample and then immediately turned to other things, unfortunately, is that particle physics is where we're exploring high energy densities, high power phenomena. So I believe that ultimately the enabling technologies that we're going to require for power propulsion are going to be derived in some fashion from developments in particle physics. Unfortunately, particle physics has not been looking in any of those directions, and so I think some opportunities have been missed because the mainstream community has been going in certain directions. There may be some return from that, and I'll talk a little bit about it in the course of the talk. But just as a metric, I want to put out a scale to talk about. If we were able to efficiently, with zero loss, accelerate just 1 kilogram to a tenth of the speed of light, it requires 108 kilotons of energy. So I want to put things into that perspective. Delos or Orion, we're talking serious amounts of energy. We're talking about an amount of energy that, if not correctly applied, is going to be ultimately destructive to whatever we're trying to accelerate. So I'm going to start with a survey on elementary particles. I know from a little bit of the conversation here and some of the conversation at Roberts last night that some of this is going to be old hat to some of the audience, some of it will be unfamiliar. Because of the time constraint, I'm going to be covering all of particle physics in probably 10 minutes so that I can get on to my conclusions. So we'll try to make it understandable, and of course I can always talk offline to anyone at the end of the presentation if you'd like more detail on any of the aspects I touch on. So I want to talk a little bit about both the particles, how we currently produce, control, and measure the results of particle experiments, and then talking about some of the developments that have been coming in theory that have not yet been fully expressed by the results of our experiments and what that means. I want to talk a little bit on the faster than light neutrino developments, a little bit on antimatter, but really the ultimate focus that I want to talk about on antimatter is where we want to go to produce it in measurable quantities of any kind that could be potentially exploited for power. This is all of elementary particles They are the constituents of protons and neutrons, and hence they compose most of the observed mass of the universe. The leptons, the electron, and the electron neutrino, which are much lighter, but balance the electric charge of the quarks. In addition, we have observed, for reasons that no one can truly explain, that these patterns repeat. All of ordinary matter is made of the up and down quarks. Find the laser pointer, it's still down here. The down quarks that make up the protons and neutrons and the electron. But when experiments and energies available in the 40s and 50s, we discovered the mu meson and the strange quark. In the 80s, we began to discover the charm and bottom quark and the tau meson. And now in the current experiments at Fermilab and CERN, a lot of emphasis has been on the top quark systems. Now, in addition to these fundamental particles of mass, there are force carriers that intermediate the reactions and interactions between those particles. The photon, which is responsible for ordinary electromagnetism, which other than gravity is the consequence of every force that we see and communicate on any scale other than the nuclear scale. Molecular interactions are extensions of electromagnetism. Friction, mechanical friction, is electromagnetism. All the way down to the individual interactions between the elementary particles that result from electromagnetic interactions. Secondly, we have the W and Z bosons, which communicate the so-called weak nuclear force thousands and millions of cycles during the course of an experiment. At designated positions, the counter-rotating particle beams are brought together in detectors such as the Collider Detector Facility at the Tachyons, where we have an array of tracking detectors in the center and an array of energy measurement detectors on the outside in order to extract particle tracks and energy and look for the systematics of particle charge due to the curvature, momentum, and energy that are indicative of significant physical developments that are worth measuring. Interactions occur thousands to tens of thousands of times per second, and some of the largest computers in the world are used to sort the results for the interactions of interest in further study. So this is the scale of the device, to go back to Les's comment earlier, that one needs to produce and work with nanograms of antimatter. We need to find a way to scale that down and a way to make it a lot more efficient if we're to use antimatter productively. Now, a little bit of combination here of dimensionality. Einstein, in 1905, of course, developed the special theory of relativity as an outgrowth of work by Henry Lorentz and Minkowski, which ultimately showed that time, as a dimension, is equivalent to all of the space dimensions. Einstein then generalized that in 1915 to a four-dimensional picture where space-time is curved by gravitation. Now, in 1921, a physicist named Klein, whose work was later augmented by a gentleman named Fallacy, figured that this process had worked so well that we could try to add a fifth dimension for electromagnetism. And I'll point out there have been some analyses on classical Fallacy-Klein theories, not quantum, that show that this could be a mechanism in and of itself for faster than light travel. So, following this process today, we attempt to account for the addition of a strong and weak nuclear force by continuing with this process of postulating that all the forces ultimately represent interactions between the particles in higher dimensions. Conventional Fallacy-Klein models, which are based on the traditional assumption that elementary particles are geometrical points, ultimately require 10 space dimensions plus a time dimension to describe gravity, electromagnetism, and the strong and weak force. String theories, which I'll talk about a little bit more in a minute, achieve that in 9 plus 1 dimension. And then, of course, there are additional higher dimensional variations as one looks at beyond the string theories. But I want to make the important point that there are mathematical congruencies that the theorists are discovering between these different classes of models, which show that, interestingly, geometric point particles in 11 total dimensions and string theories, which involve one-dimensional particles or fragments in 9 dimensions, ultimately can express the same physics. The results look the same. So keep that in mind as we try to follow the congruencies through the path of research. Talking a little bit more about strings, an ordinary Feynman diagram, which represents the particles basically as points that are followed with straight lines, in string theory is replaced by interacting strings, which are closed loops of matter, still only the one-dimensional extent, the length of the string, but the strings merge together in their interactions. So this shows a much more fluid approach. That's one reason why a lot of physicists are moving in the direction of using string theory. It has a lot of currency. Or looking in the higher dimensions where this type of structure is represented by even more complicated two-dimensional surfaces or membranes or three-dimensional solids, etc. But all of the current theories are assuming that this is based on the standard model that I described above, with the addition of a process called supersymmetry, whereby all of the current particles are paired with much more massive particles that are correspondingly more difficult to observe, more restricted in their interactions, that also that have different spin than the conventional particles. One other thing I will mention in terms of doing this is that string theory allows for finite-sized particles. They're no longer infinitesimal, which means that the infinities that come from trying to work with particles that go down to zero extent are automatically drop out of the theory. That ultimately makes the theory conceptually simpler, even though you're having to track more things in more dimensions, than point particle theories, which have these infinities that then have to be canceled by a complicated mathematical procedure known as renormalization in conventional field theories. Now, starting with my thought, I've said this privately and a few places publicly. Don't want to diss Einstein, but there is a fallacy in his logic. Ultimately, all of dynamics is a relationship between moving particles that are interacting together. Dynamics is all about a geometrical relationship. That means that it seems to be a tautology that forces can be modeled geometrically. That does not necessarily mean that force changes geometry. Ultimately, general relativity is just a model. It's an extremely good model. It has stood up to every test we've taken. And Les is telling me that I'm already running out of time. So
you got 5 more minutes for talking.
5 more minutes, yeah. Okay. So, I want to talk a little bit about the Higgs. Now, in general relativity, mass produces curvature of space-time. In elementary particle physics, Higgs produces massive elementary particles by creating a field that provides resistance to their motion, ultimately. The main point here is that the data is increasingly inconsistent with the theoretical explanations for the Higgs. If the Higgs exists at all, it is constrained to this very narrow band of mass. And people are beginning to look at models that have different ways of expressing the Higgs force, or are beginning to concede the Higgs particle may not exist in any form. And again, note that this is tied intimately to the discrepancy between particle physics and general relativity. Tachyons are hypothetical particles that always travel faster than light and are permitted by relativity as long as they stay in this region outside the so-called light cone and don't cross it. And they are said to possess imaginary mass or negative mass squared to preserve the Einstein kinematic relationship. Now, as Les alluded to again, and as I think most of you probably know, CERN and Gran Sasso have recently found that neutrinos sent from CERN to the detector at Gran Sasso are arriving about 60 nanoseconds earlier than can be accounted for by travel at the speed of light from CERN to Gran Sasso. There's a lot of consternation, a lot of people trying to find explanations. This may not stand up. I don't know whether it will or not, but I do want to point out that this is not the first time that neutrinos have suggested superluminal velocity. Fermilab's companion experiment to Gran Sasso had the same result, just before statistics. And in fact, if you look at all of the data the particle data group had in 2006, every experiment is consistent with negative neutrino mass. Every data is consistent with the idea that neutrinos travel faster than light. There may be a problem there. You will note that the particle data group only uses the two smallest values, discrepancies, and says, and even that still gives an average that is faster than light. And they wave away the rest of the data by saying that there are systematic errors. So, the bottom line, the results are not all still in, but the evidence is there. All the evidence we have says that neutrinos are faster than light. Matter and antimatter, I've already alluded. I think the main takeaway from this chart, since we're running out of time, is that the explosive potential is 43 megatons per kilogram. This gives us the power we need to meet those speed requirements that I mentioned earlier. But it's difficult and expensive to make. One theory people have been looking at are the so-called muon theories, which suggest that quarks and leptons are made up of even more fundamental constituents. These are beginning to get a lot more currency because, not because of the neutrino results, but because of the Higgs boson non-discovery. People are actually giving prions more credence. But they've been around in science fiction since 1930. And I want to emphasize that the Rishon model by Harari, probably the best known of the theories, well adapted in science fiction, well known. If you walk away from Harari's model, the fundamental components that make up the leptons and the quarks add up to be equal numbers of matter and antimatter. So in this model, which probably is still just the approximation, not fully correct, matter and antimatter at the constituent level are exactly the same. That suggests that if we could figure out how to do it, we could get matter and antimatter having exactly the same composition of Rishons, convert one to the other to create antimatter, or go directly to energy or to matter to energy conversion without the intermediate. So I'll just go to my final talking point to stop. These are the experiments that I think that we need to start looking for those possibilities. Questions?
Really, it takes 8 years to give you goosebumps, okay? So,
Yes.
Do we know where this dark matter falls in all this?
Most of the theories of dark matter are generally considering that it is some set of particles that do not interact electromagnetically or by the strong and weak force. It only interacts gravitationally. Dark matter is consistent with some of the constituencies of string theory. Dark matter is also consistent with some of the neutrino mass possibilities. I'm not sure exactly how the neutrino mass issue, if neutrinos do turn out to be conventional tachyons, how that works in the general relativity. I actually did a little bit of work with that as an undergraduate when I was working with Al Finley at Western. But I have not really had a chance to pick up on that. One of the things I would like to do, okay, I'm bankrolling for retirement, so I've got about 100 books to read and work on. Yes.
I mentioned this last night, and there is a follow-on to the opera experiment, which has been repeated twice now. There's another experiment at Branes also called Icarus. Glasgow and Norris took the data from the opera experiment, folded it back through standard theory, and found that what they're measuring, well, they're not measuring the energy, but the Icarus experiment does, is that they should be measuring an energy loss in neutrinos, and they're not seeing them in the Icarus experiment. So there's a conflict between the two empirical results now.
Well, I can't say, I'm not fully up to speed on everything that's happening. I mean, it's like everyone else here, I'm here on my own time, and this is not what I do in my day job. But I took a look at Sheldon and Glashow's paper when I ran across it, and I was not impressed by the assumptions, personally. Doesn't mean they're wrong. I mean, I'm certainly no Glashow, but there was a lot of assumptions in that paper, and I didn't walk away with a comfortable feeling that there wasn't hand-waving going along to try to explain the result away. But the bottom line is that even if they do succeed in explaining that result away, that still doesn't change the fact that it is consistent with all the other data we've got. So, yes.
Are there any of the particles in your standard model that have the parameters that sound reasonable for dark matter, as you described them? It sounds reasonable.
None in the standard model.
Is it possible to take a density, high-temperature radiation field with the standard model, let it cool, and show particles freezing out of it? Let it run a while, compare that with densities that are observed for real particles, real atoms.
I don't know that that's been done. It certainly is possible, and I can't immediately rule it out.
Yes, we're talking about the possibility of conversion of matter to antimatter,
Yeah.
and back and forth, and the possibility of just doing away with the entire thing, and just working with intermediate state. In other words, just freeing up the energy right there.
Yes.
That is exciting.
Yes.
I'd like to see that technology.
I would like to see that too. And,
Well, not on my doorstep, but yes.
I don't know. You go back to, I pulled up Skylark 3.
Mm-hmm.
You go up Skylark of Space, at least the way Smith rewrote it in 1951.
Mm-hmm.
It basically had a compilation of energy fields which resulted in the release of energy from constituent matter for propulsion. So I've been told that Doc always had some theory that he was aware of when he wrote something, but I don't know exactly what he was thinking at the time.
Unfortunately, I think we're out of time, Jim. We need to go on to the next speaker. Go ahead. Since you're-
Speculation.
Yeah.
The possibility that there might be a way to easily convert matter into antimatter, on demand, might be explanation for the Fermi paradox.
We'll talk about that during Stephanie's talk.
Yeah, thank you, Jim. Appreciate it.